Our next talk will be presented by two authors together. Jiawei Liu from, let me see, UIUC, and the second author is Jinkun Lin from NYU. And the talk is about NNSmith generating diverse and valid test cases for deep learning compilers.
Yes, talk, sorry. Okay, thanks everyone. So I'm Jiawei from UIUC, and today my partner Jinkun and I will be co-presenting our new work, NNSmith, generating diverse and valid test cases for deep learning compilers. So with the recent advance of compilation technologies, more and more deep learning compilers have been actively developed to efficiently run deep learning models over various platforms. While the compiler brings us systematic performance improvement, it is challenging to ensure its correctness. This is because the compiler stack is very complicated, as we have models of various operators, a line of passes to be applied, as well as different cogent targets. As a result, compiler engineers wrote a lot of test cases constituting a significant proportion of the codebase. Because crafting and maintaining such a huge test suite is expensive and insufficient, in this work, we aim to automate the process by performing automatic test case generation for deep learning compilers, and we built a tool called NNSmith to address this problem. So when it comes to testing in deep learning, a test case usually involves three key components. Firstly, there is the model itself, essentially a graph of operators. Second, we need to provide the model with computational inputs, including both the model-wise inputs as well as the parameters. Oh, sorry. Finally, to ensure that the model is functioning correctly, we perform differential testing to generate reference output for manifesting potential semantic bugs. Specifically, we want to generate well-formed test cases. This means that we want to generate valid models in the sense that the model itself is deemed to be compilable. However, this is non-trivial as operators cannot be arbitrarily constructed and composed to form like valid models because they have their individual constraints. For example, if we have a pooling operator whose kernel size is larger than the input size, oftentimes it will be rejected by the compiler's parser because it is invalid. And consequently, such a model cannot test other deeper and more critical components in the compiler. To construct valid models, we need to understand and resolve the operator constraints. Specifically, for each operator, we can actually define its input constraints explicitly, which are actually can be formed as a set of predicates over its input shape dimensions and the operator attributes. To illustrate, let's say for a pooling 2D operator, we can actually symbolize the 4 input dimensions, such as the batch dimension, channel dimension, and so on, and the group of attributes, including the kernel sizes, padding sizes, etc. And based on these symbols, we can specify its corresponding constraints. For example, the kernel size of the operator must be positive and no larger than the padded input size. What's more, we can actually turn this specification into code written in Python. Specifically, we declare the operator's attributes in the constructor, and we use a class method called requires to produce a list of predicates as its constraints. In addition, when checking the constraints in the requires function, how do we actually know the input dimensions, and how do we correlate them with the shape dimensions attributes in prior layers? So this requires us to also specify like how to propagate the input shapes and data type to output shapes and data types in the function we call type transfer. And with this, we get a complete specification for operator. With these operator specifications, we can now construct models in an incremental manner. That is, each time we insert an operator to the graph and maintain its well-formedness. One way to insert an operator is to perform forward insertion. Let's say we want to insert a new operator to the graph with two existing nodes here, X and A. And we first randomly select an operator type. In this case, let's assume it to be an add node, which is B here. We then find out all the plausible producers by checking if the data types and lengths of shapes are compatible to B. And then with these plausible producers, we can do constraint solving for B over the shapes of A and X, as well as the attribute inside B. And if it's satisfiable, we can safely insert B to be the consumer of A and X. And otherwise, if it's not satisfiable, we will restart the steps with other operator types. We can actually also do backward insertion so that we can generate multiple inputs for the model level. Please, I'll check our paper if you're interested. So next, please allow me to transit the presentation to my partner, Jinkun.
All right. Thank you, Jiawei, for presenting us the algorithm to generate a well-formed model. And next, to form a test case, we also need to generate a well-formed input, such that when the model is computing over this input, no single layer of this model will produce a not number or infinities. And otherwise, as we detailed in our paper, we are gonna easily miss bugs or see false alarms. Unfortunately, if we just simply initialize the input with random values, we are going to see a lot of non-numbers and infinities. But why are we seeing so many such values? Where do they come from? Turns out non-numbers happen when the input fall outside the domain of a function, such as the square root of x, which will produce a not number if there's a negative element in its input tensor x. Similarly, infinities happen when the inputs are from an unstable domain, such as the power operator, which will produce an infinity for large base or exponent. And such a phenomenon only affects some what we call nullable operators, and some examples below. Okay, so we need to ensure that each such nullable operator in the model gets safe input. This is certainly easy if this nullable operator is just the first layer of this model. But it can also be in the middle, say ith layer. How can we find the input at the first layer to ensure that no out-of-domain unsafe values are produced at the ith layer? So we cast this problem as an optimization problem and solve it with gradient descent. Specifically, we will start with a random input x and run a model until we find a non-number or infinity. Then we will specifically design a loss function for each such variable layer, such that the gradient of this loss function, after backpropagated to the first layer, can tell us how to tweak input x layer to avoid producing an out-of-domain value at this current layer. And then we just repeat the process until we see no not numbers or infinities are generated at any point. And the way we design this magical loss function is to first ask the user to specify the desired domain for each variable operator using inequalities, such as x greater than 0 for square root of x. Then NNSmith will map each inequality to a loss function, quantifying the distance of the input from its desired domain. So this non-negativity inequality will be using such loss function, which, as you can see, increases when x becomes more negative. With this approach, NNSmith is able to find none and free input for 98% of the models we generated. So putting it together, to test a deep learning compiler, NNSmith first generate a well-formed model, then a well-formed input, then run this model with this input and compare it with the expected output. And if such comparison fail with a crash or inconsistent result, then we file a bug report. So now let's look at how it performs in practice. So we use NNSmith to test 3 compilers, which are TVM, only sometime, and TensorRT. And we have found 72 bugs so far. 51 of which have been fixed. And some interesting findings below. First, most of the bugs that we found produce a crash, but they are not the only type. There are other more severe bugs that can cause incorrect results silently. We also see lots of bugs in seemingly easier phase that just tries to load or export a model. And there are many other findings. Check out the paper if you're interested. Next, to show that it does help us to test the compiler more efficiently and more comprehensively, we fast 2 compilers for 4 hours and record the branch coverage number. This is around 18% for NNSmith compared to previous state of the art. This is around 1.8x and 1.08x of the improvement. Finally, there are other works like NNSmith also trying to test a deep learning system, and they can be classified into 3 categories. And the first category is focused on testing individual operators. So they are able to find bugs related to one single operator efficiently, but as a result, they are not able to find bugs involving multiple operators. The second category is focused on generating low-level IRs to test a deep learning compiler. Doing such avoids the trouble of dealing with the annoying operator constraints because they are not building a graph. But as a trade-off, they won't be able to find bugs in graph passes. Third, there are also works that are similar to us, which also tries to generate a well-formed model to test the compiler. But they only support simple operators and connections that do not change the shape of the input tensors, like element-wise operators. So they have limited graph diversity and have fewer code paths tested, as we show in our evaluation. So to sum up, we introduced NNSmith, a well-formed and diverse test case generation approach for deep learning compilers. And we have used this approach to find 72 new bugs in real world. And we invite you to test your compiler with NNSmith. It supports multiple model formats and compilers, but if this doesn't meet your requirement, don't worry. You can easily add support for new formats, compilers, and operators. You can even customize the model inputs beyond not number or infinity free. And NNSmith is available on PyPy. It also has a nice command line interface for you to play with. And finally, we look forward to seeing you in the poster session, which will be in tomorrow afternoon. And with that, we are happy to take any questions. Thank you.